Let's look at a confidence interval problem in which we're asked to work with a sample proportion to estimate a population proportion. Our problem here says that of the last 100 days of plant operation, 60 have been injury-free. So that sounds like a sample to me, and I'm going to ask myself, what is that sample measuring? So 100 days, our sample size is 100, and if this were a sample mean problem, the thing being measured would be a continuous value, a countable thing, a measurement of something. But in this case, we're looking at each trial having exactly two outcomes, which we'll think of as a success or failure. So let's think of the success outcome as being that a plant day was injury-free, and that will make our sample proportion equal to 60 successes divided by 100 trials, or 0.6, 60%. So that represents our sample proportion for this problem, and let's go ahead and sketch that out. So in reviewing our assumptions quickly, we need to make sure that n multiplied by p, as represented, estimated by p hat, as well as n minus the complement of p hat, both of those must be greater than or equal to 5. The smaller of these will be 100 times 0.4, which is 40. That's greater than 5, so that allows us to utilize our standard normal distribution to solve for this confidence interval. Alright, we're asked to come up with a confidence interval that spans 93% of our entire distribution. So let's start this off with 60% right in the middle of our distribution. So that is our p hat value, our sample proportion of success that we observed, and that also would serve as our point estimate of the population proportion. Now let's go ahead and come up with the margin of error that's appropriate in computing this interval. Remember that that margin of error represents, in this case, the exact number of percentage units, because this is proportion, both below and above that point estimate or center of the interval that will give us the appropriate upper and lower proportion boundaries. So let's go ahead and before we do the margin of error, we'll just take a little sub-step and compute the standard error of this sampling distribution. And for any proportion problem, that standard error will be in this form. So let's go ahead and populate this. P hat is 60%, 1 minus p hat, sample size is 100, and in simplifying this, we'll have 0.6 multiplied by 0.4 divided by 100, square root that, and if we do the math on that, we'll come up with standard error of 0.0490, or 4.9%. Alright, good work so far. We now have our standard error of the sampling distribution of the sample proportion here, and that will be one of two components that is going to go into computing the appropriate margin of error here. So having just solved for the standard error, let's come up with the appropriate z alpha half value for this problem. any z alpha half value that we find is always going to be a three-step process. First step is compute the appropriate alpha, and that is going to be the complement of our confidence interval width. So 93% from 100% gives us an alpha of 7%. Next step in finding z alpha half is to split that whole alpha into two. So 3.5% of the alpha falls in this tail, and correspondingly 3.5% of the alpha falls in this tail. So next thing we're going to do is we're going to go to our z-chart and find the specific z number that has this exact amount of area to its left. Area to the left of exactly 3.5%. And when I say exactly, it's fine to round to the nearest area in the chart. So let's go to our chart. We're going to look up an area of 0.0350 on the negative side of the chart, and 0.0351 looks like our closest value from these areas in the chart. So lining that back to the left and upper indices, that's going to say that negative 1.81 is the z number that has exactly alpha half area to its left. And as we always do with z alpha half, we're going to take that negative value that we looked up and symmetrically flip it to represent the positive version of that. So our z alpha half is now 1.81. So let's go ahead and come up with our completed margin of error. So 1.81 is our z alpha half. The standard error, as we computed, was 4.9% or 0.049, and doing that final calculation here to come up with our margin of error value, we're going to multiply the z alpha half of 1.81 times the standard error value of 4.9%, and that's going to give us a margin of error of 8.87%. And now, knowing exactly how many units of percentage our margin of error is, we'll take our sample proportion, and we're going to add and subtract to that margin of error. So the confidence interval at 93% for this question is equal to 60%, which is our sample proportion of success, subtracted and added with 8.87%, and that's going to give us a final confidence interval of 51.13% as a lower boundary, and the corresponding upper boundary is 68.87%. So we can say now with 93% confidence we could expect the percentage of all plant days of operation that are injury-free to fall between 51.13% and 68.87%. Thanks for watching.